This is problem 675, Smith Van Ness 8th edition. Here we have a desuperheater. So it's got liquid water, 3100 kilopascals, 50 degrees C, sprayed into a stream of superheated steam at 3000 kilopascals and 375 degrees C. And it's in an amount such that a single stream of saturated vapor steam at 2900 kilopascals flows out at a rate of 15 kilograms per second. So assuming adiabatic operation, what is the mass flow rate of the liquid water? And then they ask, what is the total entropy generation rate for the process, and also what is the irreversible feature of this process? So the first thing I'm going to do is just put down this little schematic where we've got our liquid water being fed in. We've got our superheated steam coming in as stream 2, and our saturated vapor steam I've numbered as stream 3, and that's coming out at 2900 kilopascals and 15 kilograms per second. What we need to find the mass flow rate of the liquid water. And of course, in doing that, we're also going to find the mass flow rate of our superheated steam. So this problem is a little different from a lot of the other problems we've worked, like pumps and compressors and turbines, where they've been relatively simple systems and we have just one mass flow input and one mass flow output. And so that makes the energy and mass balance equations fairly simple. This, where we have two mass flow inputs and one mass flow output, makes the energy balance and mass balance a little more complex, but it's not going to be that much more complex. The other thing that I wanted to bring up is what is a desuperheater, and why would we want to desuperheat or cool down, basically cool down steam? And the reason is because whether or not you want to have superheated steam or saturated steam, it depends on what you're doing in the plant. As we know, superheated steam, it's going to have a lot more energy, and superheated steam is used in power plants because it has more energy. Also because, just for some very practical reasons, there's no liquid water droplets that that you won't have liquid water that is impinging at very high velocity on turbine blades that are also turning at very high velocity, and that would just cause, over time, that would just cause too much physical erosion of those turbine blades, too much damage. Another reason why superheated steam is used is simply for transport through pipes. Superheated steam is going to be less dense. It can be transported at much higher velocities through pipes, and so what that also means is that to get the same amount of steam from one place to the next, you could also use smaller inner diameter pipes, so cheaper materials used to or at least less material, I should say, to transport the steam. As well, when you have superheated steam, you don't have to worry about steam condensing and basically having a layer of water on the bottom of pipes, and so you don't need to have steam traps in and things like that. So that's why you would want to have superheated steam. However, if you are using steam for thermal applications or for heat transfer applications, where you want the heat from the steam to be transferred to another stream, and that's usually done in what we call a heat exchanger, and you'll learn all about heat exchangers in your heat transfer class that you'll take as a junior. Saturated steam will always have a much higher what we call heat transfer coefficient than superheated steam. And so you could think of this as probably due to the, for example, the density. Saturated steam is going to be denser, and it will be able to transfer its heat energy, its thermal energy, to the pipe wall, and then across the pipe wall, and then to the other fluid that you're trying to heat up much more efficiently. So you can use smaller heat exchangers, more efficient heat exchangers. Also, when saturated steam condenses, the temperature stays constant, and so the overall equipment design is a little bit simpler. Another reason why you wouldn't want to use superheated steam in big thermal process equipment is that when the temperature is higher, the usually the construction of materials is going to be a lot higher, and we're talking about more complex equipment, not just pipes that are used to transport steam from one place to the next, but we're talking about heat exchangers, which have lots of pipes, twists and bends and turns and baffles and valves and everything else that's involved in a heat exchanger. So that is why you would say, if you have a plant that's generating steam at one location, you may want to generate it as superheated steam, say to transport it way across a plant, or to have it run a turbine to extract energy. But once you reach the part of the plant where you are doing heat exchange, you would then want to desuperheat that steam, cool it down, and convert it to basically what's known as what is saturated steam for those heat transfer applications. The other thing that I wanted to note, in this problem we are specifying a saturated vapor stream coming out, saturated vapor stream of steam coming out. And the reason we are doing that is simply for ease of calculations, because we are using the steam tables. In reality, you should note that you aren't going to be right at the saturation conditions. You're going to be probably 2, 3, 4 degrees above, several degrees above superheat saturation, and that's just for practical purposes, so that you aren't dealing with condensation where you don't want it to happen. So anyway, you can go to this website if you would like to find more, or just do a Google search and you can find more about desuperheaters. Here's a little schematic of steam running through a desuperheater. It's basically just a mixing chamber here. And one of the things that I also wanted to mention, here's our cooling water that's coming in. There is a control valve. There's a control valve on this cooling water, and so the flow rate of the cooling water is going to be controlled because there will be a temperature sensor here, a temperature sensor that's measuring the temperature of the steam. So you want it to be about 3-4 degrees above saturation temperature, and there will also be a pressure, probably a pressure sensor as well. But that will run through a temperature controller, and then that will send a signal based on the measured temperature. That will send a signal to whether or not you want to open this valve more or close this valve down more to control the flow of water. And you will learn all about that in your process control course, and you may do some experiments like this in your process control lab that you will take as a senior. Alright, so that's enough introduction. So let's go ahead and let's reintroduce the problem here. Here is our schematic reproduced here. We want to find the mass flow rate of the water. We list our assumptions. We're going to be assuming that this is steady flow conditions, steady state, so there's no change in time with our system. We're also told, remember from the problem statement, that this operates adiabatically. So it's not that it's perfectly insulated. In reality, there will be some heat loss, but for our purposes, we're going to assume that the heat loss is negligible. Another word that you might see in other books for adiabatic is well insulated. If something is well insulated, that's another way of saying that it's adiabatic, or that heat loss is negligible. Also, there's no work being done, right? There's no moving parts, no expansion, contraction, or anything like that. The only work that we're concerned with is the flow work, which is captured in the enthalpy term. And as is probably obvious, we do not need to worry about kinetic and potential energy changes. Those are also going to be negligibly small. So we've already talked about the fact that we are going to have to use energy and material balances to solve this problem. That should be fairly obvious to you by now. But also realize we're going to need the entropy balance. So let's bring up these equations first before we go any further. Our material balance, accumulation equals in minus out. There is no accumulation, of course, and so in is equal to out. So our input is m.1, m.2, and our output is m.3. All right, and remember, we know what m.1 we know what m.3 is. We want to solve for m1 and m2. Our energy balance, there's no accumulation, so our input is m.1 times h1, enthalpy of stream 1. Our other input that we have to add is m2 h2, m dot mass flow rate stream 2, enthalpy of stream 2, and then minus our output is m.3 times h3. And I did not write the Q. There's no heat transfer between our system and our surroundings. Also, there is no work. So Q and W are 0 in this term. I didn't write them down. Now our entropy balance. Our entropy balance, this is from chapter 5. Remember, it's a little bit different from how we do a material or energy balance. Because remember, entropy is not conserved. Entropy is not conserved. So we don't just have the 0 equals in minus, accumulation equals in minus out. It is different. Our total entropy generation rate, and this is outlined in your text, so make sure you go through it. Our total entropy generation rate is equal to the accumulation within the control volume. That's what this term is, plus our delta. Now, and so this is where it's a little different. Your entropy balance is a little different from here. So here we have our output as positive here. So this is our M3 times S3 minus our inputs. All right. So go over the derivation of those equations again if this is confusing to you. But you need to remember that our entropy balance is a little different than our energy and material balances because the fact that entropy is not conserved. And remember that to satisfy the second law, this entropy generation rate has to be greater than 0 for a real process. And remember, if it's equal to 0, then it's isentropic. And we're talking about theoretical process there. All right, so let's start at the simple. Let's not worry about the entropy balance at the very beginning. We'll deal with that later. Let's start easy. Let's start with the material and energy balance. So we know M3, right? We do not know M1 and M2. If we look at the conditions given to us, we're given temperature pressure for stream 2, and we're told this is saturated vapor. So basically the properties or these streams are fully specified, and we should be able to look up H1, H2, and H3. So if I take a look at these two equations, I see I have two unknowns, M1 and M2, but I know H1, I know H2, H3. So I have two equations and two unknowns with my material and energy balance. So what I should be able to do is just use the material and energy balance, solve for my two unknowns, M1 and M2, and then I should be able to plug all those numbers along with S1, S2, S3 that we can look up in the steam tables and get my total entropy generation rate. So that's how I'm going to approach solving this problem. Start with material and energy balances, then move to the entropy balance. So the first thing we need to do is we need to start assembling our properties. And so I'm going to look at, we're going to skip stream 1 for now because there's it's a little more complicated. Let's start at stream 2. This is easy. It is superheated steam. We're given the pressure. It's a nice round number, so we can go to the superheated tables and look that up pretty readily. That's on page 708 if you're following along in your textbook. We can look up the enthalpy, H2, 3175.6 kilojoules per kilogram. And I went ahead, while we're at it, we might as well write down the entropy, even though we're going to solve that later. Stream 3, this is saturated vapor. So saturated vapor, that means it's fully specified at 2900. We can go to the superheated steam tables at 2900 kilopascals, nice round number. That also is on page 708, just a index above. And we can look up the enthalpy of stream 3. That's of the saturated vapor, 2802 kilojoules per kilogram, 6.1969 kilojoules per kilogram Kelvin. So that's the easy part. What about this liquid water, 3100 kilopascals at 50 degrees C? Is this saturated water? Well, if you don't know the answer right off the top of your head, what you'll have to do is you'll have to go to the steam tables and figure that out. 3100 kilopascals, 50 degrees C. If we go to the steam tables, we find, and in fact it's on page 708 as well, we find that the saturation temperature is 235.67 degrees C. That's a lot higher than 50 degrees C. So what that means is this stream 1 is what we call subcooled water. And I don't know if your textbook has mentioned that term, but that's what we call what we call liquids. And most liquids that we deal with in real life, water that comes out of the tap, and whatever other liquids that we happen to deal with, any kind of fuels or gasoline, motor oil, cooking oil, they are all subcooled liquids. The problem is we don't have steam tables for subcooled liquids. So what do? Well, there's a couple things we could do. One of the things we could do is we could go to the internet and we could see if someone happens to have tabulated the properties of water at 3100 kilopascals and 50 degrees C. It would be great if they did, right? And if you are working on this on your own and you want to use that as a resource for solving this problem, that would be fine. Just make sure you document it. Make sure that you are using a reputable site, and make sure that you are careful with the units. One of the things, for example, is that our textbook puts everything in absolute pressure. So you need to be careful. Some of the steam tables out there will put things in gauge pressure, and so there will be some differences. So if you had those steam tables, those property tables for subcooled water, that would be great. But if you're using the textbook, we don't have that. So what can we do? Well, we can go back to chapter 6, and in equations 627 and 628, that is on page 215 in your textbook, they go through these property relations for liquids. The little section heading is alternative forms for liquids. And they give you these two equations, 627, 628. This tells you that you can calculate enthalpy based on heat capacity data, and remember this beta, which is the volume expansivity that we introduced back in chapter 3. This is heat capacity and equation of state information. So what this means is we could integrate this and calculate a delta H as a function of temperature and pressure. We could calculate delta S for a liquid, say from T1 to T2, P1 to P2. So that's what we are going to use to solve this problem. Now, how do we actually do this in practice? Well, this is where a little bit of thought needs to come into play. And so I've got this explained here for you. So the way that I would approach this problem is I would say, okay, what is going to be the easiest way to solve this problem? And the easiest way to solve this problem, and kind of thinking from it backwards, but what this volume expansivity, we're going to have to integrate, we're going to have to figure that out. And this volume, what are we going to do about that? what I would do is try to avoid dealing with this term here. So the way that you can do that is we could say, okay, we're going to start at 3100 kilopascals and 50 degrees C. That is going, let me back up. We're going to start at 3100 kilopascals and the saturation temperature of 235 degrees C. We know what the saturation enthalpy is, right, of liquid water at 235 and 3100. So that will be, you can think of that as our H1. Then what we're going to do is we're going to keep the pressure constant, and we're going to raise, or we're going to drop the temperature from 235 to 50 degrees C. If I keep the pressure constant, this dP term goes to 0. Also, this term over here goes to 0, right? And what am I left with? I'm left with delta H is equal to Cp, or dH is equal to Cp dt. If I assume that heat capacity is constant, then I have delta H is equal to Cp delta T. And I can use that to then calculate the enthalpy of subcooled water, because I know the enthalpy of water at the saturation temperature. So if you need to pause it and think about that, that's fine. But let's push on ahead and let's actually do the calculation here. So what I've done here is I've just tabulated, I've just put down, this is the enthalpy of saturated liquid at 3100 kilopascals, 235. I also wrote down the entropy of saturated liquid, because we're going to have to do that calculation as well. And then what I did is I looked up the heat capacity of water. And this is by now you probably have this memorized, but I am also here assuming that the heat capacity of water is constant. I am not doing a polynomial function of heat capacity, although your book does give you that option in, I believe, Appendix C or B, something like that. But we are just going to, for this problem, assume that heat capacity is constant at 4184 joules per kilogram Kelvin. So then I can integrate this equation. Delta H is equal to the integral of Cp dt. I'm going from T1, which is my saturation temperature, to my T2 is my 50 degrees C. And notice I put everything in Kelvin just because I'm working in MathCAD. If I do this integral, I get a delta H of minus 776 kilojoules per kilogram. My delta H is equal to H1 minus H2. I want to solve for H1, and so that is equal to my enthalpy of saturated liquid, which is this right here, plus my delta H value. And so from that I can calculate my enthalpy of my subcooled liquid. H1 is now my enthalpy of my subcooled water at 50 degrees C. And you can see it's a lot less than my enthalpy of saturated liquid water, which is at 235 degrees C. So that makes sense as far as that goes. All right, so I can do the same thing with entropy. I do the same calculation with entropy, and I integrate. Now I'm integrating Cp over T dt, and I'm letting MathCAD do everything, but notice I'm still integrating from my saturation temperature to my subcooled temperature. And so I get a delta S of minus 1.9 kilojoules per kilogram Kelvin. I solve for my entropy of my subcooled liquid, and I get a value of 0.762 kilojoules per kilogram. Now I've got a few notes up here. I've got a couple sentences here. If you look at the publisher's solutions, they do this differently, and I think it's a more complex method. You can read through this, but what they do is they do it a little bit differently in that they hold the temperature constant and change the pressure. So they go to the saturated steam tables, look up 50 degrees C, and then, and by the way, the saturation pressure at 50 degrees C is 12.34 kilopascals. That's really low, right? And then what they do is they say, okay, let's take this temperature and hold the temperature constant and go from this pressure to 3100 kilopascals. So what they do is they hold the temperature constant, so that means the dT term in these equations goes to 0. And now they have to integrate this term, this right term, the right term in both of these equations. And there's nothing wrong with doing that. The problem is that you are going to have to calculate a beta value. You're going to have to calculate the volume expansivity of liquid water. And of course, you're going to have to assume that's constant. So you can do that. You can go to the saturated steam tables and you can look up the saturated liquid volume versus temperature, and you can make a little table of those values, and then you can do a graph and do some linear regression, and the slope will give you the beta value, right? You can calculate the beta value from the linear regression. That's perfectly doable. It's just going to take some time. Right. The other thing you're going to have to do is you're going to have to calculate you're going to have to look up the volume, right? You're going to have to look up the liquid volume. And of course we can do that, but then when you integrate this, you are going to have to assume that that volume stays constant. And remember, we did a problem like that in, I believe, in chapter 3, where we assumed that the volume was constant. Another thing you might do to make this a little more accurate, the volume, the molar volume or specific volume is going to be different from 12.34 to 3100. So maybe you use the arithmetic average of the volume at those two conditions when you do your integration. So that's another way to do it. And if you look at the published solutions, they get values that are pretty close to what we got. But the way we did it here, by keeping pressure constant and integrating with temperature, a lot easier, and I think probably has the potential to be more accurate, because probably heat capacity being constant over this pressure range is a lot more reasonable than assuming that volume and beta are constant. All right, so that was a lot of work just to get the enthalpy and entropy of subcooled liquid, but now we know how to do that. So now all we have to do is we have to solve our material and energy balance equations. So I've written them here again. I've written now, given us our given information, and so you can solve this using the just regular old pen and paper and some algebra. You could easily do that, but since we're using MathCAD, let's go ahead and use a solve block in MathCAD. So to do that, the first thing you do, and if you're doing this in Excel, whether Excel Solver or however you want to do it, a lot of these solver routines, you need to enter an initial guess. And so I know that it's not going to be a 50-50 split, but let's just go ahead and do that just to make it easy. So I just said, okay, we have a total mass flow rate of 15 coming out. Let's just say we have 7.5 kilograms per second coming in. So let's set up our solve block now. It's using the given statement. So given is a specific MathCAD command to tell that we have a solve block. And so I just copied and pasted these equations using the Boolean equal or the control equal here for defining my equation. So my material balance, my energy balance, and then my find, because I have two variables, I'm now going to use the array or vector format in MathCAD. And so what I'm doing now is I'm saying, okay, let's assign M1 val, this is a new variable, to what it finds for M1, M2 val for what it finds for M2 up in these equations here, because everything else is known. M1 and M2 are my unknowns. So I do that, and then all I have to do is I can just see what M1 value is. That's 1.9 kilograms per second. That is my mass flow rate of the subcooled water. And then my M2 val is 13.1 kilograms per second. You can eyeball that and see that they check, but it's always good to check your work. So we just set up a little equation. Yep, 15 kilograms per second. We also just copied and pasted our energy balance equation, let it plug the numbers in, and we got 0 watts. That's what we should have gotten. So that checks. Now we're able to solve for the entropy generation rate, and so that is just taking our entropy generation equation, plugging in the M1 and M2. Notice that I've now changed it to M2 val, M1 val, because M1 and M2 are defined as unknowns here in MathCAD. M2 val and M1 val have the values. Actually, M1 and M2 were the guesses, I should say. M1 val and M2 val have the answers. So we do that, and we get a total entropy generation rate of 1.97 kilojoules per second. We could write that as kilowatts per Kelvin. And the value is greater than 0, which it should be according to the second law if this is a realistic process. And the book also asks you, what is the irreversible feature of this process? And that should be fairly obvious to us by now. The irreversible feature is we're mixing cold water and hot water, and that's just not reversible. We can't spontaneously unmix cold water and hot water and have the cold water separate from hot water in the pipe. So this is a desuperheater, and hopefully you've gotten a little bit. The way the book gives it to you, it's a pretty sterile landscape as far as how the book presents this information to you. But hopefully you've seen a little bit now of why superheated steam is good in some cases, but not in others, and why saturated steam is better for some applications than superheated steam. And you've got a little bit of a flavor of how these desuperheaters actually work, and a little bit of a preview of the kinds of process control problems that you may be working on in, say, the junior lab, or the senior unit ops lab, or your process control lab.